So in this video, we're going to look at different methods of generating electricity. And we're also going to take a look at how we work out the efficiency of a process to generate energy. Okay, so let's start off with defining what efficiency is and show how we calculate it. So we need to define a few types of energy before we can explain efficiency. So the first thing we need to understand is what we consider useful energy. So we have lots of different processes we harness as humans, so like things like combustion or batteries, there are things like that. So useful energy would be the things that those processes produce that we actually want or that they're intended to make. Wasted energy would be types of energy we get that we weren't intending to make. And quite often that would be in the form of thermal energy. And when you use the input energy, that's the amount of energy we put into a given process, and then that is transferred into both the useful and the wasted energies. So using conservation of energy, which means energy cannot be created or destroyed, if we put some energy into a process, we must get exactly that amount of energy out of it. Some of it would be useful, some of it will be wasted. And efficiency of a process is the ratio of the useful energy transferred to the amount of energy we've put into the system. That's efficiency. Okay, so we've defined what efficiency is. Let's see the different ways we can calculate. So we give efficiency in two different forms. One form is as a decimal, the other form is as a percentage. So as a decimal, efficiency is just the useful energy divided by the input energy. That's what ratio of useful energy to input means. If we express that as a percentage, all we're doing is multiplying that answer by 100%. And that gives us efficiency as a percentage. So with any given process, you cannot get more energy out than you put in. So that gives you a limit of, for a decimal efficiency, the biggest number it can be is 1, or a percentage efficiency, the biggest it can be is 100%. And if you get a different value or a value above those, you know you've done something wrong. So that's calculating efficiency. So let's have a look at an example. So say we've got a 15-watt bulb and it gives out 12 watts of power in the form of light. So what we want to do is work out the efficiency as a decimal and as a percentage. And we're going to do that by determining how much energy is input and how much is usefully transferred in 1 second. So we're going to use our equation for linking energy and power. So we put 15 watts in. So if we do that for 1 second, that's going to dissipate 15 joules of energy. So we've put 15 joules in. We get 12 watts of useful power out. So if we times that by 1, that means we've transferred 12 joules of it to the form that we want, which in a light bulb would be light energy. So the symbol you can see in the middle of your screen is the symbol for efficiency. So if we want it as a decimal, it would be useful divided by input, so 12 over 15, which has the value of 0.80. If we turn that into a percentage, all we're going to do is we're going to take that 0.8, times it by 100%, and we'd say it's 80% efficient. So based on the numbers we've seen there, we can see that 3 joules has been wasted or transferred into a form we don't want, probably in the form of thermal energy most of the time, which corresponds to essentially 20% of the input energy. So 80% useful, 20% wasted. So you might be wondering well, how did we decide to multiply it by 1 second? Well, let me show you what happens if you decide to use a different amount of time. So let's say we do it for a minute instead of 1 second. So to get the energy, we'd multiply the power by 60 because it's 60 seconds in a minute. So you can see we get input energy of 900 joules. We get useful energy transfer of 720. If we calculate the efficiency with those values, we see we get exactly the same number, 0.8, which gives us an 80% efficiency. So as long as we use the same time for both the input power and the useful power, we can see we get the same efficiency, so it doesn't actually matter which unit of time we used. Okay, so that's how we calculate efficiency, let's look at one of the methods we use to visually represent efficiency in the form of a Sankey diagram. So this allows us to show the energy transfers that are going on and also the quantities into the different types. So we saw from the previous example that we put 900 joules of electrical energy in because it's a light bulb, and we got 720 joules of useful light energy out, and you can see that represented by the dark arrow there. So we can see that using conservation of energy, we must have wasted 180 joules of energy as thermal energy to the surroundings there. So you can see because that's a smaller value, it has a smaller arrow there. So this is how we can represent energy transfers and efficiency using a Sankey diagram. We do it with the values and the size of the arrows there. Okay, so that's how we actually illustrate efficiency using a Sankey diagram. What we're going to do now is take a look at a few methods we can use to generate electricity. And with each of them, we're going to look at some of the key facts about it and also describe the energy transfer occurring in each method. So the most common method that we use at the moment is using coal, oil, gas, which are collectively known as fossil fuels. And they're called that because the fuels themselves are formed from animal and plant matter that died thousands of years ago. So it's literally made from fossils. So the reason they became a fuel is because underneath the earth, they're subject to very high temperature and pressure, which transformed them into a large quantity of chemical potential energy. And chemical potential energy is essentially the energy stored in bonds in a material. So there's a lot of energy stored there. So for example, if you have 1 kilogram of natural gas, it holds 55 megajoules of chemical potential energy. Oil is very similar, but slightly less, it's 48. And coal, again, slightly less, is 30 megajoules. But it's a colossal amount of energy in 1 kilogram, which is why it's very commonly used. So in terms of the energy transfer, we can see then all of those three, we would start with chemical potential energy. And what we do is we burn that, which is the fancy name for that that scientists use is combustion, the process of releasing energy by igniting it. So that turns the energy into thermal or heat energy. And we use that to vaporize some steam. And then that then spins a generator, which turns it into electrical energy, but we also get some wasted energy in the form of thermal energy. And in a power plant, there will be something like 30–40% of the input energy wasted as thermal energy to the surroundings there. We only get about 60% useful energy. So that's coal, oil, and gas, or fossil fuels. And as we know, these fuels, when we burn them, release CO2 into the atmosphere, which results in the process we call global warming, which is raising the average temperature of the Earth fairly significantly. That we're looking at 2 to 3 degrees by the end of the century at the moment. So that's the downside of using these fuels. And the other problem is that they're going to run out. So oil has less than 30 years of supply left, gas something like 20 years, coal a bit longer, but coal is really bad, so we don't want to be using that. Okay, so that's our fossil fuels. The next we have something called biomass. So fossil fuels are dead animal and plant matter that died thousands of years ago. Biomass is recently dead animal or plant matter. So wood from trees would be an example. So once we chop down a tree, we kill that tree. So it is definitely dead, but it's very recently dead. And we can do it with other things as well. We can harness it from plants, from like bacteria or from dead animal, that kind of thing. There's different ways we can get energy. But we still typically burn that thing to generate the electrical energy. So, for example, wood, which is a type of biomass, you can see 1 kilogram holds 16 megajoules of energy. So again, a lot of energy, not quite as much as the fossil fuels, but still a good amount. And we release the energy in exactly the same way. We burn it, to produce thermal energy. We use the thermal energy to vaporize steam, which spins a generator to generate electrical energy, and we still waste lots of thermal energy. This is actually even less efficient, something about 50% efficiency. The benefit of using wood is that it grows back much more quickly than fossil fuels. If we're using something like bamboo, it can grow very quickly in a matter of a few years. Fossil fuels take thousands of years to make, so wood is better because we can regenerate it faster, but it doesn't give us as much energy. Talk about the big bogeyman of electricity generation, nuclear power. This is probably one of the most misunderstood types of energy by the general public. So nuclear power in essence releases nuclear potential energy, so energy stored in the nuclei of atoms, and it does it by splitting the atoms using a process called fission. We literally split one nucleus into two nuclei, releasing energy. And 1 kilogram of uranium holds 80 terajoules of energy. So we saw 1 kilogram of oil has about 50 megajoules. This has 80 million megajoules of energy. So the amount of energy is colossal in nuclear fuel. And the process is very similar. So nuclear potential energy is turned into thermal energy using fission, and then we generate electricity in exactly the same way, and we still waste quite a lot of energy as thermal energy to the surroundings there. So as we've seen, uranium is great because it's a massive amount of energy, but building a nuclear power plant is incredibly expensive. We're talking billions and billions and billions of pounds. And the other problem with nuclear decay is we produce radioactive waste, which takes thousands, if not millions of years to become safe. So we have to spend a lot of money storing and keeping our radioactive safe. And generally speaking, people are scared of nuclear power. People have seen the nuclear bombs in Japan during World War II, and they've seen the disasters like Chernobyl, and they are very scared of nuclear power, which is why a lot of people are not in favor of it. But on the plus side, a large amount of energy from it doesn't make any CO2. Now we're going to look through some of the what we call clean or renewable types of energy. So the first one we'll take a look at is solar power, which takes light energy from the photons of light arriving from the sun and transfers them into electrical energy. And theoretically, the sun delivers 12 terajoules of light energy to the Earth every second, or 12 million megajoules every second. So we could harness a colossal amount of energy if we use solar well. So the process to turn light energy into electrical energy is called excitation. I'm not going to go into any more detail than that. It's something you study more at A-level. But we still get, as per usual, wasted thermal energy. So from the amount of energy we've seen there, we have the potential to supply the whole of Earth's energy needs with solar power easily. But solar technology is quite expensive. It can only operate during the day because obviously there's no sunlight at night time. And if we get any cloud cover, that can also massively decrease the amount of energy that we generate. So it does have some fairly significant downsides, but the potential is very good and the price is decreasing over time. So that's solar power. The next quite common one we see is wind power. So wind power takes the kinetic energy from air particles in wind, and it turns it into electrical energy when the wind turbine spins. So it spins a generator and we get electricity. So from recent estimates, I had a look at some studies to find this value. There apparently are about 95 terajoules of kinetic energy available in wind every second. So again, there's enough energy out there to supply the whole of Earth's energy needs, but it's not very reliable. So if it's not windy, we can't get any wind power. So it's very unreliable. And the other thing is people don't like seeing a wind turbine near their house. Apparently, I don't understand that one at all. I think they look awesome, but that's just me. But the the transfer process we get for a wind turbine is kinetic energy from the air. The air particles collide with the wind turbine, which causes it to spin. So we've still got kinetic energy, and then that spins a generator and generates the electrical energy and also some wasted thermal energy there. So that's the energy transfer process. Slightly less common, but still large potential, is wave power and also tidal power. So wave power takes the kinetic energy of water particles from waves. Tidal power takes the kinetic energy from water particles due to tides. So they're quite similar in that they harness energy in the same way, but we use them in different scenarios. But again, just like before, there is a colossal amount of potential energy to gain from these technologies there. But to harness tidal energy, we have to build massive dams across river estuaries, which it can be very damaging to a local wildlife, so people are very opposed to that. And wave power is very much a new technology. It's not very widespread at the moment, and having all of this technology out in the sea, again, can be a danger to wildlife. But just like wind power, it's essentially turning kinetic energy into electrical energy, and still wasting some thermal energy there. Hydroelectric is currently in quite a boom. There have been some massive hydroelectric dams opened in Asia, in Africa, and there's been some for many years in North America. So essentially, these dams transfer gravitational potential energy. So you've got water, generally speaking, at the top of mountains and other places like that, and they turn that into electrical energy, because what they do is they allow the waters to fall and turn their energy into kinetic energy, and then that collides with the turbine to generate electrical energy. So this one, I struggled very much to find a figure for how much we could generate globally, but one hydroelectric power plant can in theory generate 22.5 gigajoules of energy every second. So again, there's colossal potential for getting energy this way. So like I said, it starts off with gravitational potential energy. We've got water that's relatively stationary at the top of a mountain because we've trapped it up there with a dam. We let some of it flow through and turn into kinetic energy as it falls, and then that water then collides with a turbine to generate our electrical energy there. So it can be great because we can essentially switch this power station on and off very quickly. We can decide whether we let water flow or not, but it's very expensive to build these big dams, and there's also quite risk to the environment from the dams themselves because they flood the surrounding region when they build them, which can have an impact on local wildlife. Again, something that's not too common, but is starting to be explored more. There's quite a few of these being built in the south of France and in other countries as well. So geothermal, as it sounds, takes thermal energy and it transfers it into electrical energy. So it works the same way most power plants do. It uses the thermal energy to evaporate water into steam and uses that steam to turn a turbine. And so this thermal energy is coming from deep underground. So it's from the core of the Earth being heated by what's going on in the mantle and the core. So we're getting stuff that's deep down is very hot, and we can take that energy and use it to our advantage. So there's a large quantity of this energy available, but it can be very hard to access as we have to dig very deep underground, which is expensive. It's only available in certain locations on Earth, and again can damage the environment around the plant. So it's a very simple power plant because we just already have the thermal energy. We don't need to generate it, but we can't harness all of it usefully. Some of it becomes electrical, but some is just sent into the surroundings as thermal energy there. So to summarize, we generally put those methods into two categories. We either have fossil fuels and nuclear power, which we describe as non-renewable because once we use that fuel, it will take thousands of years to replace it. And we describe things like solar or hydroelectric as renewable because when we use them, it doesn't deplete the amount of energy available there. It's always being replaced. It's always windy. More rain is developing, so the hydroelectric dam refills itself. Things are always dying, so we always have biomass. So those are always available to us and are constantly being replaced, so we call them renewable. So at the moment, most of our energy comes from fossil fuels and nuclear power. Different countries have different balances. So if you go to Scandinavia, they have a much higher percentage from renewables. In France, they have a much higher percentage from nuclear power. In America, they have a very high percentage from fossil fuels, for example. But this is something we're trying to change. And those of you who watch the news will know or may have heard about the Paris Climate Agreement, which sets out very strong targets to use more renewables and decrease our dependency on fossil fuels, which are releasing CO2 and causing global warming, and are projected to cause massive rises in sea levels and global temperatures, which all the countries in the world have agreed to, except one. Literally every country in the world, including ones that are war-torn, has agreed to the Paris Climate Agreement, but not America, for reasons let's really not get into. So that's kind of where we are at the moment. Where we're going to finish off this video. So we've had a look at the efficiency and how it can be represented, and each of the different types of electricity generation and the energy transfers involved. If you have any questions, please feel free to comment and ask me. I'll happily get back to you. But thank you very much for taking the time to watch.